Hi, everybody, and welcome to Physics 4B. Today is the 24th of February. Today is a new chapter, actually. The first chapter, you guys remember, had to do with the electric field, okay? It's actually, we introduced Gauss's law, and we did the switch, really, kind of mathematical trick, but at the end, it's really a real physical concept. It has meaning. You can measure it in the lab. So the electric field is not a mathematical construct. It is really a physical concept that you really can test in the laboratory and work with it and so on and so forth. And as some of you already were talking about the fact that we were dealing with triple integral, at least the form that I gave it to you was in triple integral. The promise, again, is not to do the actual triple integrals. Okay? The promise is you use one thing or the other, and you boil down the problem into a single variable, basically integration, which is something that you should have seen either in Calc 1 most likely, and you don't know how to handle it. You know how to handle those things, so there's no problem with it. Today is actually going to be the introduction of Gauss's law. Gauss's law takes advantage big time of the symmetry in the problem and lifts the integration completely into some sort of a simple calculation. Okay, problem becomes algebraic altogether. Now, as I said before the recording started, if there is no symmetry in the problem, then you better find other ways of finding your electric field, okay? The next chapter actually will introduce the concept of the electrical potential, which makes the problem somewhat easier in a sense. Remember, these three chapters are really a hunt of the same thing, the electric field, okay? So the first chapter was dealing with it in its full-fledged form, looking at it exactly how it's supposed to be, okay? This chapter, chapter 22, would take advantage of symmetries in the problem and somewhat comes up with another way of finding the electric field in those situations. Instead of having to deal with these difficult integrals, if there is symmetry, then you can get away with it and you can solve stuff easier, okay? The third thing that we're going to do in chapter 23 is going to be the electrical field. Remember the potential field, the electrical potential, okay? The electric field is a three-component vector in space. So it has an X component, a Y component, a Z component, three components in space. And these three components in space depend on three variables also, depend on the in and out, depend on left and right, and depend on up and down. So each component of the E vector depends on X and Y and Z, okay? This is in the case of electrostatic. In the case of electrodynamic, there is a parameter T also. So it's going to be 4 variable functions. So the problem can be ugly and complicated, and probably you're going to be turned away from it because of the difficulty in it, okay? Now, chapter 23 says, instead of dealing with this 3-component vector, namely vector E with its X components and its Y components and its Z components, you're going to deal with a number, a scalar function, namely the electrical potential, which is a number, which is a function that depends still on X and Y and Z, but it's much easier to deal with one number rather than with 3 vectors, 3 numbers, okay? So that is the advantage of chapter 23. And again, you're going to get the electric field out of it, okay? So all of these 3 chapters, really, they're going to teach you different ways of finding the electric field, to put it in the terms of what Mr. Feynman put it one time in one of his live sessions, basically, that we want you to be empowered with all kinds of basically techniques and methods trying to solve problems. And if one doesn't work, maybe another one works, maybe another one works when you are really in the field and trying to solve problems, okay? So you try one technique, the other one, the third one. If it doesn't work, then basically one of them ultimately will be easier to handle than the others. So those are the 3 chapters so far, okay? That has 22, 20, 21, 22, and 23, how they are basically laid out right now, how they are basically structured, okay? You're probably wondering, I mean, isn't this complicated enough? And you just mentioned a 4th variable, time t. Well, we're going to deal with it when its time comes into a place, okay? I hope that you guys are not scared from what I'm saying. I'm just laying it out as it is. I'm telling you the truth. I'm not going to basically cut corners for you and cheat you out of your education, because I don't feel that's appropriate. In other places I have seen people basically go to the first problem and the second problem from the back of the book, which are easy, plug in the numbers basically. Here is Q1, here's a Q2, here is your distance R, and find F. If that's the case, that's probably you're sitting in the wrong class, and there are some supposedly calc-based courses that do that. And I personally don't find that this is really how should I put it, conducive to a more complete learning, especially if you're going to really be in the field and expected to solve real problems, okay? I hope you guys appreciate what I'm doing. I work very hard to make this concept as approachable as possible, and hopefully you guys would work with me to do the same thing, okay? Okay, where is my pen? Any questions so far? I know one of you guys had a question, and I'm not sure if he's here or not, but about the recordings, and I just saw what that person was talking about, and I made sure that in Confer Zoom I deleted all the recordings from before because they were confusing. There were several recordings, and because basically Confer Zoom records and basically times and then records and times, so the person was confused the order, which one is first, which one is second. And to answer the question, actually, there is a timestamp that Confer Zoom puts on each one of the sessions. So if you look carefully in there, you will see that there is a date and time on it. And time, it uses a military time. So you can see the order there. But just to remove any confusion, I just deleted all of them, and I refer you back to the discussion where I post the recordings. Okay.
Thank you.
Okay, no problem. Somebody was wondering about the lab today. Most likely there will be no lab because we are not ready for the content. Unless you guys want to do a session, I will be more than happy to sit with you guys and discuss these things in there, okay? So we're gonna wait for the lab afternoon to see exactly what's going on, okay? We'll see how we will progress in here, because I have problem 55 and problem 52 from this chapter that I want to do with you. Those are the minimum problems we will do in this today. I mean, in this chapter. In the past, I gave problem 53 also, which is identical like problem 54 from this chapter as exams, okay? So 52, 53, and 54 in the past, I administered them as exams. When we do the magnetic field, there will be similar stuff. There will be something similar to Gauss's law when we do the magnetic field called Ampere's law, okay? During that time, if I don't address these problems now, we're going to address them later. And as a matter of fact, you probably saw these problems also when you were dealing with the moment of inertia and the center of mass in physics 4a. And the method is called the method by subtraction, basically. You subtract stuff, and there is a technique that is a beautiful technique, actually, when you're trying to find the electric fields and things like that. Imagine yourself, the situation, you're an engineer, and the cable that you're using, for example, for fiber optics or something happened to it, it's torn, or a mouse came and chewed from it and deformed it, and all of a sudden the signal is not going properly, correctly in all of the places. So instead of having to actually do the actual complicated integral trying to find the signal every which way, so what you do in this case, you assume that the signal is the tube is some sort of a cylinder. You do a calculation, and I'm going to tell you what it is. So Milo has a question, which is a very good question, which I don't remember the exact name. I think by subtraction, or by the method is by subtraction. So what you do in this case, Milo, and everybody else, so we're interested in the method for problems 53 and 54, and probably we're going to do one of them. I'm hoping to get into one of them at least. One of them is cylinder, the other one is a sphere, so the symmetry is a little bit different. So you assume that there is no cut in the cylinder, and you solve it. And now you assume that there is basically there is a distribution of charge in here in this case, or distribution of current in the case of magnetic field, and you solve for that for the entire undisturbed basically cable. But then you go to the place where you chew from it because it's really missing, and you assume a negative distribution in there of charge, or current moving in the opposite direction if it's a current, to simulate the fact that there is no charge in there or no current in there. That is this method basically, and you solve for that, and you add using the superposition principle in this case, and you add, and you can find a good simulation to what happened to your signal, for example, while it propagates around that area. Okay, obviously we're not going to do this problem. That's actually more of a hands-on real field problem if you're an engineer. And actually I dealt with something like this one while I was in a different country, actually, working with some engineers who came to me. I was actually teaching this stuff there too. And one of the engineers who was working in the oil field, basically, they were dealing with the pipeline for the oil. And sometimes the oil, the pipeline has issues. So what they have this basically this probes that go all the way in, and they give them a readout into basically the electrical properties and all kinds of properties of the pipeline. And sometimes it gives them false readings because they think that the pipeline is damaged. So what they do, they dig inside and they find out that the pipeline is not damaged and it's too costly of an operation. So there was a similar problem, albeit it has nothing to do with the mouse chewing on your cable in this case, but different conditions in that thing in there, and usually it has to do with other things. So that is something that is a little bit different. But the point in here, as engineers, you deal with the situations, and sometimes technicians also, you deal with the situations, and you would want to address them, you would want to fix them. So you don't need to be especially on Mars to really solve problems, but you could be actually on the field and deal with these things and trying to have solutions for them, okay? So that is problem 53 and 54. And I'm hoping to get to one of them. It's a simple method actually to do this. And I think if I did physics 4A for you guys, I would have done something similar also when we do the moment of inertia and also the center of mass. Does anybody remember having done a similar problem like this one, those classes?
I do remember the moment of inertia and all that, yeah.
But you did the method of the subtraction, trying to find the moment of inertia, for example, of a sphere and a hole in it somewhere.
I did it with a bowling ball, like something like that, where it has like a solid center and then like a hollow shell.
Okay, that is the method of subtraction. That is similar to problem 53, 54. And down the road, when we do problems, when we do the magnetic field too, okay? So that's beautiful. You guys seem to be on shape, great shape, okay? So let's get going with this chapter 22, and the promise that it holds, as I was talking to you about. So hopefully we can get this thing going too. And let me share with you a screen. Share. OneNote, chapter 22. Okay. So the analogy with the first of all, the electric field so far. Let's take the point charge, okay, and then we will see what we can do for a general distribution of charge. So here is a charge. I saw last time, if you guys remember, that this charge will have an electric field that points every which way in all directions, okay? And we could come up with a representation of the electric field as it is coming from this one in here, okay? One way of doing it actually is coming through the entire space and bring your test charge and draw another line in here, and then that's probably supposed to be longer than the first line, and another one smaller, and so on and so forth, and another one smaller. So this is complicated, isn't it? Because now you can have a longer wire in here, same thing in here, which is a little bit more than that, but less than the first one, and so on and so forth. So that is one way of representing the electric field. If you're worried about the negative charge, it's the same thing, except everything is pointing in the opposite direction, that's all. So if I have a negative charge, the electric field in here will be very strong, whereas in here it's going to be slightly less than the first one, but more than probably this one, and so on and so forth. And it's everywhere, okay? So that is how the electric field is represented in this case. These are the representation of the electric field, and this is everywhere, okay? Every single point in space, you're going to find the electric field lines that are the field actually that is pointing in there. This is one representation of the electric field. Actually, this is not a good representation of the electric field. There is a trade-off that we're going to use. So, for example, when we did the dipole, we have a negative charge in here and a positive charge in here. And I did not do that completely, but this is what is expected. The electric field will leave the positive charge and come to the negative charge in here. And every single point in here that I can find the strength of the electric field. And this line, I expect it to follow this path. Again, because it emanates from the positive charge and ends in the negative charge always. Think of this one as some sort of a source, the water faucet, and this one is the sink, okay? So this is the source, and the other one is the sink. And here, it's going to go around, curve around this curve, and come all the way to this side. Okay? On this side, this field lines where they're close from the charges, they're long. When they're further away from the charges, they become smaller. That's basically the point in here. Same thing in here. This one is going to come in here and go around. I'm not going to stretch, and then it's captured when it comes back and comes in here. There is one field line in here that seems to go from here and continue becoming smaller and smaller as it goes around, and then goes all the way toward the edge of the universe, because this is parallel in the same axis. This is the one that we calculated last time, and we calculated one also here. You guys remember, it's the same calculation in here too. I didn't do that, but if I did it this way, it's going to be pointing this way. Okay, which is actually the signs will flip. That's all in there. Okay, and in here. Okay, so this is the field way representation in here. This is similar to the magnets actually. Okay, that is another way of representing the electric field, in this case using geometry. Here is the alternative to this vector representation, and that is just to draw a line, because between each point and point there is a point. You guys know that. Between this point, for example, where I draw the first field line, the second one, there is another point that I could draw the field line that is going to be longer than this one, but shorter than this one. And between this point and that one, there is another point in here that is going to be longer than this one, but shorter than that one, and so on and so forth. As a matter of fact, between this point and this point, there is another point. Do you guys understand that this is continuous and goes for infinity?
Yeah.
So instead of doing this vectors, which kind of tedious, we're going to do another representation now. So we're going to take the electric field in here and draw a whole line, saying that, hey, between every 2 points, there is a point, and that is endless. So I'm going to draw a whole line, end of the story. And there is another line in here, there is another line in here, and there is another line in here. As a matter of fact, between these two lines, there is another line in here, because the same analogy will happen in here, and it happened in here, and it happened in here. For the case of the positive charge, this line is a straight line that is going to come out, end of the story. If it is a negative charge, it's going to point in the positive, and oops, all of a sudden I have flipped the signs in here, okay? If it's a negative charge, if this is negative, this will point in here, and it extends to infinity, this extends to infinity, and so on and so forth. And the same idea in here is this way. So that is another way of representing the electric field, and these are called actually the field lines. Well, we lost something in the process. We gained something. We gained the fact that the electric field is defined everywhere in space, which the other one could not really represent to us, because this one, there is a discontinuity. It looks like there is no electric field in here. But the representation tells me that there is an electric field everywhere, and that is a plus. That is good. What we lost actually is the strength of the electric field, because in this representation near the charge, I have a longer wire and a longer arrow than further away from it. So this one tells me about the strength of the electric field. This one does not, because it's just one line. You guys understand? So we gained one thing, we lost one thing. How to compensate for what we lost to make it also clear? Here is what we do. We promise to draw a number of field lines per unit charge. So let's say, for example, we agree that, okay, we're going to draw 16 lines for 1 coulomb. So if somebody has 2 coulombs, we're going to draw 32 lines. Do you guys understand? If you only have half coulomb, we're going to draw only 8 lines. Do you understand? So that is the convention, just to regain that knowledge that we lost before, because in the first representation, it had that detail. It had the strength of the electric field closer, than the other one. So this was telling you about how strong the electric field was. This representation cannot tell you that because it's just a single line going extending from the charge all the way to infinity. And the electric field clearly here is a lot weaker than in here. Do you guys understand? Yes?
Yeah.
So that's a detail we lost. We gained an information that we didn't have before in a sense that there is an electric field defined everywhere in this line. And as a matter of fact, everywhere in space, okay? But this one in here, now we'll regain that knowledge if we agree to draw a certain number per charge. Now we're gonna say this. Okay, if I have 1 Coulomb, I'm gonna draw a certain, I'm not gonna draw 8, okay? 16, it's too many for me to draw. So I'm gonna draw 4 instead, okay? And say it's only 4. So I know that there is a 1 Coulomb in here. If you decide, you know what, I want to have 2 coulombs, then I'm gonna draw 4 more to tell you that now the field actually is emanating from a stronger electric field charge. Okay? If you decide to have 3, I'm going to have 3 times 4, which is 12 lines, and so on and so forth. If you decide, and so on and so forth. Do you guys understand the thing? I may have to readjust them a little bit to keep them symmetrical, because 12, you have to adjust it a little bit. So you have to take 360 degrees divided by 12 and adjust the angles correctly to keep it symmetrical. But that's another issue as long as you keep the proportions correctly. So now we have 2 details in here. In other words, the field is defined everywhere, at least on that line. And also we have retained the strength of the electric field by the so-called the density of the field lines. What I mean by the density of field lines, if I take a sphere in here, this is by the way in 3D, not in 2D, okay? I know I'm drawing it in 2D. If I take a sphere in here, and, or no, not necessarily sphere, if I take an area in here, okay, of square meter squared, and count how many field lines. I will find 2 in this case. Then I know that the field lines are denser in here. That means that this is how much field lines I have. I have 2 per square meter. Now, if I make this area a lot smaller, like this one, I'm counting 1, 2, 3, 4, 5, 6, 7, 8. So I know there are 8 field lines per square meter. I'm assuming also this one is a square meter. So if I'm going to take this area and make it as compact as possible, so it's the same with square meter, but it's very close to make that, that effect, then I'm going to end up with more field lines per square meter than further away. Do you guys see the challenge? If I move further still, I can here still carry that 1 meter square with me and count how many field lines penetrate this one. This one is going to diverge in here. The other one is going. So how many field lines now do I have? I'm down to
just 1.
1 field line per meter squared. So in here, I think because I'm saying the strength of the field depends on this density, the field is weaker than in here, which is stronger than up close, which is stronger even still. You guys understand? This is the way that we're going to we recover the knowledge that we had before, namely the fact that we have how the electric field is represented with this so-called field lines. Field lines are continuous. What I was almost going to call field lines in here is not. So if I look at the dipole again, this is how the dipole field lines would look like. So this is a negative charge, this is a positive charge, and this is 1 field line going like this. And always comes from positive and ends in negative. So the arrow has to point this way, okay? And one that goes like this and comes back in here. And this one goes to the edge of the universe and come back in here. And this one, there is another one in here that is going, and so on and so forth, okay? So this is the field line representation of a dipole. Okay, if you have 2 positive charges, for example, the situation is going to be a little bit different. So we have 2 positive charges. So I have a positive charge and a positive charge. This is not a dipole, by the way, but you have 2 charges. So the field line will leave from here and will leave from here, both of them. It's going to leave from here, but it cannot really end in here because both of them are positive. It's going to try to make it to the other one, but it cannot. Same thing from the bottom, and it's going to look like this. This is a representation, basically, of the field line for two positive charges. It's clearly that these two charges are repelling one another. Okay, they try to push their field lines to one another, but they cannot because the field lines are going to basically push one another. Okay, if on the other hand you had actually twice as many charges in here, some of them will actually end up in here because this one will not. Basically, they will have less charge. So there is an effect in here. This one will overwhelm this one and push still stronger fields closer to this one than in the middle. Okay, so you'll find them probably in here when they start to diverge. In other words, this electric field will be a lot weaker in here by the time it reaches this point, because although there are two charges, but the distance plays a role, 1 over distance squared, whereas this one, it's very close from it, albeit it's a weaker charge, but it's a closer distance. So at some points, it's going to push the fields back, okay? But not in the middle. Does this picture make sense to you guys?
Yeah.
Okay, since I mentioned earlier a water faucet and a sink, there is an analogy actually with the fluid dynamics, okay? Let me tell you about the fluid dynamics, how the situation is. I have a hose in here. I'm doing a mathematical cut in it here, okay? And there is a flow of some sort. So the fluid is moving with a velocity v in this direction. I'm not going to draw the vector, but you guys clearly see which way it's moving, okay? I'm going to take an area now, a square meter in here. So this is an area A. Let's make the algebra a little bit easier for me, okay? The width is W and the height is L, okay? So the area A is LW, okay? So in this case, I'm interested how much volume of fluid will pass. It doesn't matter, in amount delta T, for example. After delta T, the fluid that passes this point in here is delta X. Do you guys see that? If I wait a delta T amount of time, this is how much fluid has passed. So what I say in this case is the amount of fluid is going to be, amount I mean volume, okay? Is going to be the area times delta X. Do you guys agree that this is the amount of fluid that has passed?
Yeah.
In delta T amount of time, in delta T. So the rate now of fluid flow is going to be simply this volume divided by the amount of time. And this is exactly the velocity, so it's AV. So this is what we call in hydrodynamics flux of the fluid. Basically, how much volume of fluid is going. If you go to a river that is rushing at high speeds, this value will be high. If, for example, you carry with you 1 meter square and you see how much field water will go on very fast flow, you're going to collect a lot of water in it. Whereas if it's running very slow, very smooth, then in this case, you're going to collect less. So this is what we call the flux in fluid dynamics. I'm going to take this area now, I'm going to tilt it a little, just to argue that this is actually not anything else but actually dot product. Let me show you what that means. So it's the same flow, same fluid. After it passes through this area A of width W and height, I put it L in here. I'm sorry about the notation here. I'm going to, so the rate at which this fluid is moving is going to be exactly AV. Okay, so what I'm going to do now, I'm going to look to another area in here. I'll probably use a different color just to make it easier. So I'm looking at this area now of the same width as before, but tilted a little. Okay, tilted a little. So do you guys agree that the same fluid that passes through the first one must pass through the other one? I don't have any sink, or I don't have any faucet in here that is dripping water in here or fluid in here, okay? So in this case, the AV that passes in here must pass in here. Do you guys agree?
Yeah.
So it's the same amount. But now it passes through a different area. It passes through this area, which is clearly bigger than the first one. So let's find this quantity now and see what's going on. First of all, the area A prime. It's going to be W times now this height L prime. L prime. I'm going to assume that this angle is theta. The tilt, okay, is theta. Can you find the relationship between L and theta and L prime? Do you guys see in this right angle triangle? This right angle triangle, the hypotenuse is exactly L prime, and the adjacent is L. So the relationship between L and L prime is that L is equal to L prime cosine theta. Yes or no?
Makes sense.
Yeah, I can see it.
Yeah.
So so now I can express that L in terms of my old L. In other words, I know exactly how this area is related to my old area. In other words, A prime is equal to W times L prime, and L prime is just L over cosine theta. And that is A over cosine theta. Okay? So that is the old area times cosine theta. Okay? So this flow is the same that is flowing in here, and it can write it now. So this, by the way, and now the A, I can write A, the old area, as being basically A prime cosine theta. It's the same thing because that's the tilt with which, and that's why I think A is less than A prime, because cosine theta at most is equal to 1, and that is 1 theta is equal to 0. So it could be, actually, this angle can be, if you put it 90 degrees, you're going to collect no water. Do you guys see that? If you take this area and you slide it right on top of the fluid, there is no fluid that's going to cross it, because now theta is 90 degrees. Okay. Yes.
Yeah.
Yeah.
So I have to be careful with this experiment. So this is the fluid. I'm going to use the symbol phi for the flux. Basically, that is how it was used in hydrodynamics. So we're going to say phi is equal to A, and A is, by the way, A prime times V times cosine of theta. Let's look at this relationship in up close in here and see what's going on with it. I'm going to look at this area in here. The vector V is this vector. That's how I started with it. The area in here is actually a vector too. I mean, it depends on the orientation. It's the cross product of the length times the width. I don't know if you did that in math already or not in calculus. What is it, in vector calculus or not, but it's very easy to argue that the area actually is a directed quantity. So this is the area A prime, actually. Its direction is perpendicular to both L and W. In vector calculus, the area A prime is a vector whose direction is given by, according to the right-hand rule, which one is the first? L, is it actually L cross W? Okay, L cross W, where L is one side and the other one is the other one, okay? Because, okay, here is the reason why the area is a vector. Can I get a paper in here that has nothing in it? This is an 8.5 by 11 paper. So its the area in here is exactly 8.5 times 8.5 times 11. Okay, but I can orient it whichever way I want to. So if I give you just the magnitude of the area, you have no direction which way the area is pointing. You guys agree? It could be pointing this way to you, or it could be pointing the opposite to me, or it could be tilted at an angle, or it could be tilted to the other one. Just to give you the speed that you're doing 50 miles per hour does not tell me anything about your velocity, because you could be moving in any direction. So the area is actually a directed quantity. It has a direction, and the direction is given by the right-hand rule, okay? The direction is given by the right-hand rule, because it's cross product, as a matter of fact. So when you do vector calculus, you will see that. Okay. So anyway, the area is that vector A prime. What is this angle now? Between V and A prime. How is it related to theta? Let me draw it in a clearer way so that you guys see it. Here is theta. Here is A prime. Here is V. I want to know this angle in terms of theta. Let me show you something that you probably cannot see right now, but I know that you know from your geometry class. This side and this side, do you guys see that they are perpendicular or not?
Yeah.
And this side and this side, they are perpendicular because that's the direction of the area. It's perpendicular to both sides, both of its sides, okay? Now I have two angles, sides are perpendicular mutually. What is the relationship between these two angles from your geometry class?
Be the same.
It should be the same, yes. Okay. Here is an easier argument for it, okay? An easier argument without using that theorem. So if this is theta, and this is V, I'm going to extend V a little bit. So this is the complement of that angle. So this is 90 degrees minus V, minus theta. And this is the perpendicular. So this is 90 degrees. This angle and that one also add up to 90 degrees. Do you guys see that? Because this whole thing adds up to 180 degrees, yes?
Yeah.
So this and this add up to 90 degrees, and this add up to 90 degrees because this is a right angle triangle. And therefore, this is actually theta too.
That makes sense.
Okay, so if you're not convinced with this one, there's a theorem from your days when you were doing geometry. That is when two angles have mutual sides perpendicular, the two angles are the same. This is an easier argument for it. And whatever you do, convince yourself that that is actually theta, okay? That this angle is theta, because it is, okay? Then the flux then can be written as follows. Phi is equal to the area A prime times the vector V, because this is simply the dot product of two vectors. The magnitude of the first, A prime, times V, times the cosine of the angle between them, because theta is the angle between V and A prime. That's it. So in the first case, the only reason why you ended up with AV is because the angle was 0 exactly, because the area was pointing this way and the velocity is pointing in the same direction, so the angle between them was exactly 0. That's why cosine of 0 was 1. That's why you ended up with the flux being AV. In the second case, when you tilt the angle a little, it's going to be just the new area, which is A prime, times the velocity V, times the angle between them. So this is how we define flux in fluid dynamics, and that's how we're going to define it now in electrical fields. So we're going to define, by definition, phi E, which stands for the electric flux, as simply being E times A. If E is uniform. Meaning, just like the velocity earlier, if this is E, just multiply it by the area A, and you know what's the flux in here? Phi of E. Okay? You guys see that?
Yeah.
So it's simply as that. But if it's not uniform, then I have to really be careful, because if E has this weird behavior like this and probably like that, then, which is possible, then I'm going to take an area in space and calculate the flux in that point, d phi E, which is still E times the area that I take, this area dA, which is a dot product still, okay? And then integrate throughout the space that I care for. So the flux in this situation is going to be the integral over a surface, and I have to be careful in here, and I know I just introduced the double integrals. You're not going to be doing double integrals in this class, at least if we can help it, and we are, unless you have that mouse that you your wife, then you have to deal with that situation. But in general, that is how the flux is, because you have to sum through this area. So if this is the area actually where you're calculating the flux, the surface S, that is really the integration that needs to be carried through. Okay?
Sounds good.
What this is...
Does that only work if it's orthogonal?
No, as long as you know the cosine of the angle. That is the beauty of doing the argument before.
Oh, okay.
Yeah, you have to take that angle into account. Okay? That's the argument.
Okay, yeah, that makes sense.
Okay? So you have that cosine of the angle between them. That is a nightmare. I mean, the whole thing is so that you don't do this calculation, actually. Okay? But the analogy with the fluid dynamics takes me to the dot product in here, which I need to define a flux in general. This is the electrical flux. Down the road, we're going to define a magnetic flux also. What this is telling me is how is this electric field is flowing in a sense. If it's a fluid, okay? It's not fluid, it's not water. But how many field lines I'm calculating? This is what the flux is calculating, actually. To bring it back, it's computing how many field lines is crossing this surface. So the flux is a measure, the electrical flux. The E flux is a measure of the density of field lines. Because there's going to be a number of field lines per unit area. Remember, this area came into play in here. So that is how it's connected to the field lines, and the reason why we introduced them, to have an image for them. If these are the field lines, this flux will tell me how many they are crossing it. You guys see that? Yes?
Yes.
Yes.
Okay, so that's basically how we define the electric flux. I know there are some problems, and the first 2, 3, 4 problems, actually, they give you an electric field and a surface, and you would want to find it. Case in point, for example, if you have this weird surface in here, okay? I'm going to make up a shape in here. It's not really that weird, but somehow, for example, there is a field line crossing it in here, and another one coming it in here, and another one in here. And think of this one as coming through this surface, actually. It's coming not outside, okay? It's coming through the cube in this situation and trying to find the field line. The flux in here is going to be 0. The reason why it's going to be 0, first of all, in this area, the area is pointing this way, and this side, the top side. The area is pointing up, and the field is going, I drew it in the x direction, okay? Or at least one of the directions that are perpendicular. So the flux is 0 because the dot product of a cosine of 90 degrees is 0. So that's easy. I also did not draw it parallel to this area, so this area also is 0. So phi in here is 0 for the electric field, and phi on this surface is 0. And that is a property of the dot product. It has nothing to do with anything else, because I'm assuming that the electric field is in this direction, and this angle here is in 90 degrees, so cosine of 90 degrees is 0. So I'm done with this surface and the opposite surface. And the top surface and the bottom surface also. They are all 0 by the way I drew it in here, okay? How about the flux in this side? Well, that is not 0. The flux on this side, here. Here is how that area look like. The area, remember, is pointing actually by the right-hand rule this way. So this is the area. And the field, I drew it this way. So the flux in this case is going to be the number of field lines that penetrate on this side. If the electric field is uniform, it's going to be some value, but it's going to be a negative value. As a matter of fact, the way I drew it is going to be E times A with a negative sign, where A is that area. Height times length, okay? So if you're curious, what is the unit for the flux? Well, it's just a Newton over Coulomb times meter squared. That is the unit for the flux in here. It doesn't have a name. If you discover something in physics, they will name it after you. The magnetic flux has a name, though. They call it a Weber, okay? But this one, just a Newton meter squared per Coulomb. That's it. Now, the reason why I'm drawing this example in here, because the flux on the other side is going to be exactly the opposite of this value. In other words, in here, the area is the same, but in magnitude, and it's in the same direction as the electric field. So in this case, the flux on the other side, on this side, on the positive side, is going to simply be E times A. So if you're curious trying to understand how much flux in general through this cube is going to be 0. Because the other surfaces, there is no magnetic flux whatsoever, no electric flux whatsoever. On the other side, there is one negative and one positive, and at the end, they tend to be 0. That is because of that cosine of 180 degrees or a cosine of 0 degrees. So that takes care of this sign. This is provided the electric field is uniform. If the electric field is not uniform, well, we have a problem. Okay. If the electric field is not uniform, then we have a problem. So that means that there is a value of the electric field on one side that I multiply by it, and there is a different value on the other side. So when I add them up, the flux, the net flux is not going to be 0. You guys understand that? So the net flux may or may not be 0. If the electric is non-uniform. Okay? So that is basically what's going on in this situation. So let's try to understand. It's like, for example, you have a conduit of water, and you would want to find the flux between two regions in here. If there is no hole, no sink in the conduit, or there is no faucet, somebody is pouring more liquid to it, more fluid to it, then the fluid that comes in is equal to the fluid that comes out. So there is no net flow at the end, because it comes in, goes out. So at the end, there is no net gain or loss of fluid in that area. But if there is a sink, then you count how much water came out from the other end and how much water came in to begin with. You're going to find a missing number in here. You're going to find a net negative flux in this case, situation, and you say, "Oh man, I have a sink somewhere, okay, in this region." Or if you have a net gain, you say, "Wait a minute, now I have actually more fluid than when I started with. I have this many cubic fluid coming in. Now I have this many cubic fluid coming out. That means that I have gained fluid now all of a sudden." Okay. So that is the same thing with this example. So the flux now is really calculating how many field lines. If all of them come in and leave without any additional field lines, because if I have a source in here and that source is pushing more field lines this way, then in this situation, I can tell you that I have something that is pushing, more charges are actually pushing that. So what is the cause of this field lines are actually the charges, remember. We started with the charges that would define our field lines. So let's find the flux of a single point charge first, okay? So I'm going to take a point charge, and I'm going to go around it in a sphere. So this is a sphere, okay? And I want to find the flux over a sphere. So I know that the area of the sphere in any given point, dA, is radial. Okay? And I know the electric field also is radial in anywhere in the surface. Okay? So it's clear now that the electric field, first of all, for a point charge E, is 1 over 4 pi epsilon naught times the charge divided by the distance squared. Well, this is the distance squared, by the way, times the radial vector. The area in this case is going to be dA of a sphere, an element of a sphere, so a patch of it. So this is a patch area in the radial direction. So when I do the dot product, the r hat times r hat will just give me 1, because those are unit vectors. So the flux, element of flux on a patch of area, d phi, of the electric field on a patch of area is simply equal to 1 over 4 pi epsilon naught times q over r squared times the element of area itself, dA. And if I integrate now throughout the entire sphere, and this is a sphere, by the way, where r does not change. So on a sphere, r is constant. That is what the definition of a sphere is, by the way. R is constant. So when I'm interested trying to find the flux of the electric field over that sphere, phi E is simply going to be, this constant comes out of the integral. So it's going to be 1 over 4 pi epsilon naught times q over r squared, because it's constant. The integral, now it's a closed integral because I'm doing actually an integral over a sphere, which is closed. So this is a closed integral over a sphere of dA. And the integral of dA is A itself. So all I'm left with is find the area of a sphere, because that's actually what it is, the area of a sphere now. So what is the area of a sphere? You see, the beauty, we didn't do actually the double integral. So now we can actually Google this stuff, and what is the area of a sphere? You guys know?
4/3 pi r cubed.
That's the volume.
Oops.
Take
So,
the derivative.
so it's just 4 pi r squared.
Yeah, 4 pi r squared. Okay. That is an area. So that's all there is to it. So I'm going to sub in there for it. So first of all, I have 1 over 4 pi epsilon naught times q over r squared. Now times 4 pi r squared. You guys see some cancellations?
Everything cancels except for the q and epsilon naught.
Everything, guys, is gone except the q and epsilon naught. So the flux of the electric field over a surface over a sphere is q over epsilon naught. That is, I use the sphere for a sphere. Now, what if it's not a sphere? Let's see what the flux is. Okay. I'm going to make a simple argument for it. Okay. So let's go back into the original thing and have still a q. But now the field lines are in here. So if you're curious how many field lines cross this sphere, it's q over epsilon naught. Okay. As simple as that. Okay. Because I have a q charge. If I double q, now I have more field lines, twice as many as before. So let's take another area now. This is a closed surface in 3D. This is like not open. Okay, think of it, your basketball inflated, for example, deflated, for example, and now it has a weird shape, but it's closed still. Okay, so that's basically, it's still a closed surface. Okay, now I want to find the electric field. Now the area now is no longer easy to find, because the electric field actually will change from point to point. It's further away in here, so it's 1 over r squared, and it's closer to this point, so it's 1 over this r squared, which is closer, and so on and so forth. There are two components now first of all, the electric field always radial, but the area itself can twist and turn. In doing so, it will have two components in it, and I did not write the polar coordinates in here, which will be very easy to do to argue the case. It will have a radial component that is proportional to r squared, and a non-radial component, basically, actually two components, okay? One in the azimuth and the other one is in the other direction, the other two angles, that are perpendicular to the radial direction. When I do the dot product, those two, they don't contribute none. They contribute 0 because of the dot product. Cosine of 90 degrees is 0. So what is left then is the radial component, and the radial component will have an r squared in it. So when I go back into my expression here, what is it, dA? This dA, only the radial component, because I will have an r hat from the vector itself, E, and it will have 3 components for the area, 2 of which will be perpendicular to r hat, and they don't contribute. The only one that contributes is the one that is coming from r hat, and that is proportional to r squared, which will cancel this r squared. So at the end, I would be left with an integral over theta and phi in polar coordinates, and those theta and phi, regardless, they're going to give me 4 pi. And that is actually what's going to cancel the 4 pi. So I'm not going to do the math in here because it's really long and tedious, and at the end, it's going to give me the same result. And the argument for it is, also, you can make the argument as follows. Take a sphere, okay, of radius r, and find the field density. Remember, I just argued that this is the field density. If there are this many field lines pass through the sphere, they must pass through any shape that you can think of. Like this complicated, for example, shape of a deflated balloon, for deflated basketball, for example, okay? So they're going to pass through that many too. So at the end, the flux over any surface, not just through a sphere, is going to be Q over epsilon naught. So the flux over any surface, it has to be closed though. Any closed surface, which is by definition EDA, is equal to Q over epsilon naught. This is a definition of the flux, by the way, for a point charge. Okay. What if I don't have a point charge? What if I have two of them? How am I going to handle the situation? And you probably know the answer to it. What if I have two charges? Charge 1, Q1, and charge Q2. And I have this surface in here that is complicated. What is the flux for these two charges? What should I use? There is something that we're going to invoke in here.
Superposition principle.
Thank you very much. Have a nice day. That is exactly it, okay? So in superposition principle, what I do in here, I'm going to find the flux, ignore this charge first completely, as if it's not there. Find the flux due to this charge, phi of the electric field due to this charge, which is going to be Q1 over epsilon naught, by the way. And find the flux for the second charge, as if the other one doesn't exist on this very same surface, which is going to be also another Q over epsilon naught, but it's the other Q, not this one, over epsilon naught. And then add them up by superposition. Okay? You guys see that? Now, if I have a bunch of charges, whether continuous or discrete distribution, then all I have to do is just add this quantity, because clearly in here the denominator is the same. I'm doing this thing in a vacuum or in space or in air, so the epsilon naught doesn't change. So all I'm saying in here, add these charges. So the flux in general, phi E, which is by definition, I'm going to just write it for one more time. So any closed surface does not have to be a sphere of EDA is going to be just the sum of all the charges that are enclosed. The reason why I'm going to say enclosed is because there is a danger with charges that are not enclosed, okay? All of them. Let me argue for the charges that are not disclosed for one point charge, okay? Let's say, for example, I have a charge in here, sitting in here, and this is outside of this closed surface. And the field lines that are going to leave this point charge are going to look like this. So this, they will never intercept, but this one will intercept. It comes in through the surface, and now I have to count it. Actually, it's negative when it comes in from this side, and it's going to come out on the other side. You guys see that? So this field line will also come in through the surface at some point in here, for example, penetrates it, and it's going to leave it in here. So anything that comes in must leave the surface, okay? Always. So the net field charge for any charge that is not enclosed is 0. So phi of E is 0 for charges outside of the surface. I know some of you are more math inclined, and they will probably think of some weird shapes where maybe there looks like the surface will come in and will never leave. I mean, the field line will come in and never leave. But that's not going to be the case, because there is actually a theorem in geometry that argues for the, the manifolds and all of that, that there is no way you're going to have an odd number, basically, of surfaces. It's going to always be in pairs. Let me tell you what that means, okay, for those who are curious. Let's make this surface, for example, deflate the balloon and make it look like this. Just simple case, okay? and there is a field line that penetrates the surface at some point, comes out. I already accounted for the one that came in and left. And there is no way you're going to just tilt this one enough so that it's going to come in and never come out. So if it comes in from the other side in here again, so it's going to come out again, okay? So in either case, it's going to be in pairs. So no matter which way you tilt this one 1,000,000 times and make it look like I don't know, the bed, for example, when it's not completely made, okay? The bed sheet, it's still the same. But as long as it's a closed bed sheet, okay? It has to be wrapped around it, okay? So that's a bad example from the bed sheet. I don't know what example I should give in here that is completely messed up. But still, they come in pairs. So at the end, when it charges outside, there is no contribution to the electric flux in this case. So this is Gauss's law. Okay. Gauss's law also can be written as follows. The flux over any closed surface of E dA, that's this integral basically, that's what the flux we mean by it, phi E, is 1 over epsilon naught times the integral over a volume enclosed by that surface. You're asking, what are you talking about? Which surface it is? This surface, okay, of rho dV, okay? So that's basically another way of saying the charge enclosed. It looks ugly, doesn't it? But that's not how we use it. We don't use it this way at all. So let's find a way that we can find the electric field using this thing and come up with a prescription. What time is it? We still have plenty of time to basically use this theorem properly, because as I said before, this is actually useful only when there is symmetry. Because if there is no symmetry, you're dealing with an ugly integral in here, first of all, on this side, and then also on this side too. You didn't gain anything. As a matter of fact, you made it far harder on yourself probably to deal with the problem by doing this side of the equation. So you could have just dealt with this one using the chapter 21, okay? So in the case of symmetry, yes, you can work this problem. So let's do that. I'm going to take a wire in here. Long wire. An infinite wire, okay, mathematically infinite. Basically what it is a wire that is very long compared to the sizes that we are. We're going to come in here and find the electric field in there, E. What is the electric field near the wire? And the wire has a charge distribution, so we take a Q and sprinkle it everywhere uniformly on the charge, on the wire. So we take a charge Q and uniformly distributed. That means that the charge has lambda, which is equal to the charge divided by the entire length. I just said that it's a very long, basically an infinite wire, but it's still then it's an infinite charge on it, okay? So this is coulombs per meter is the unit for this charge distribution. So this is the charge distribution, and this is a linear line charge distribution, okay? The symbol for it is lambda in this case. I want to find the electric field in that point E. So I'm going to use the symmetry and avoid doing any kind of calculation basically as far as the integral, and at the end it should be straightforward, okay? We should be able to find the electric field faster using probably a simple integration to find everything in here. So let's do that. So for that, we're going to invent something that did not exist in this problem. So I'm going to come at a distance, which I'm going to call distance y, or r, or a, whatever you want to call it, from the wire, and find the electric field. So that's the question. E at a distance y. So basically, y is given, and we want to know what the electric field is. So that's basically the problem. So y is part of the problem. Lambda is part of the problem. Epsilon naught, the medium, is part of the problem. So those are things that I expect them to appear at the end. Anything else should not be there because anything else does not exist in the problem. So what I'm going to do in here to solve this problem, I'm going to invent something that is actually not part of the problem. I'm going to make a Gaussian surface in here. So what I'm going to do in here, I'm going to go around this wire and make a cylinder in here of radius y on a length that is convenient for me, that I chose to be of a length L. So L is not clearly part of the problem. So I should not find an answer that depends on L. Otherwise, I have a disaster before me, because if the answer depends on L, then it depends on your choice of this so-called Gaussian surface. So you guys see the problem in here. I'm choosing something that does not exist in the problem so that I can carry my calculation, because I need a surface to integrate this stuff over. So the surface that I'm going to add in here is made-up surface. It's not real. So this is a made-up surface. Okay. The answer should not depend on the stuff that we add. The answer should not depend on L, in other words. Y, yes, but not L. Okay. And I'm going to make the case, first of all, this surface has, this surface, which is the Gaussian surface, has three sides to it. First of all, it has this side, A, which is just pi A y squared, and has this side to it, which is the same size also, A is equal to pi A y squared, and has this side to it too, so the lateral surface. Think of the can, for example, that you open, and you cut it somewhere, and you open it, it looks like this. When you open it, length is L, and this side is the circumference of the circle, and circumference of the circle is equal to what? 2 pi times the radius, and the radius is y. Yes? So this is my lateral surface. Of a cylinder, which is just 2 pi YL. Do you guys agree?
Yeah.
So that's basically what I did. I made up a shape that does not exist part of the problem. We added to the problem so that we can carry that integration. Once we do that, then we know the charge enclosed divided by epsilon naught, and then we're in business. We know what this thing look like. We know exactly what the answer is for the electric field, okay? So on one side, I want to find the flux. On the other side, I want to find the charge divided by epsilon naught. Except this charge is linear distribution. Since I took an L length of it, I know the charge is going to be lambda times L. So the other side is lambda times L divided by epsilon naught. So it's easy to find the charge enclosed, because the charge enclosed doesn't count for the charge that is outside of this Gaussian surface. Only the charge that is enclosed in here. So anything outside should not contribute to the flux. So on this side, the flux I know is exactly going to be charge enclosed with charge times unit length, and it will to L in here for this cylinder, and that L will enclose then lambda L divided by epsilon naught. So on the other side, I know exactly the answer to it. Okay. On the left-hand side, and depends on L, which is really bad news. Okay. So let's check the other side now. EDA. First of all, it's a dot product. I need to get rid of these vectors. So here is the argument. I'm going to argue in here that the electric field, first of all, is perpendicular to this shape. It's in this direction. In other words, it's in the same direction as the area, this area, 2 pi YL, the lateral surface. The reason why it has to be that way, because you argue to tell me, no, it's not actually that way. It's actually tilted a little, okay? One way. Because this wire is an infinite wire, I can take it and flip it around. And then if you argue that it was pointing this way, it's going to be pointing in the opposite direction. That is because of the symmetry. Because this is an infinite wire. It doesn't matter where I am on the wire. If you argue and tell me, you know what, I think the direction of the electric field is this way. This is how the electric field is pointing. I'm going to take this wire while to tell you close your eyes. Okay? If you close your eyes and I switch the wire and I have to ask you, is the wire changed? You say, no, the wire stays the same thing. It has the same distribution. Everything looks the same. But now the electric field will be pointing in the other direction. Do you guys see that? Because if I flip the wire in the other direction. So in this case, since there is no apparent change to the original problem, then the effect in this case should not change. Why the electric field? You argued is pointing this way. Now it's pointing the other way. So this argument is not correct. The only case where this will hold that argument is if it's pointing away, up in this direction, perpendicular to the surface, basically parallel to the surface of the lateral surface. Then if you switch it around and you look at it again, the electric field does not change direction. It stayed up. Do you guys see that? So that holds that argument of symmetry. Correct?
Yeah.
Yes. So now we know that angle is 0 degrees, number one. So this is cosine of 0 degrees. So I'm dealing just with the scalars. Furthermore, I'm going to argue that the actual electric field is the same everywhere on this surface. This is the same value everywhere as long as I am on a y direction away from it. And you say, you know what? I know. I can argue, actually, as a matter of fact, that the strength on this side is less than the strength on this side. I tell you, hold on a second, close your eye for a second. I take the water and shift it a little bit, move it a little bit. So if your argument was true, and you were saying that this is more than that, this one moves in here, and now this one will be less than the other one. So now there is a shift in value in there. And I asked you before that, do you think the wire has changed? It's an infinite wire. It's a very long wire. So if I move it one way or the other, it doesn't matter. So the strength then, the only way that holds this the argument is E is the same on everywhere on this lateral surface, and is always pointing away from it in the same direction. So E is constant on that surface, and it's pointing at 0 degrees, so it's going to come out of the integral. See the beauty of this argument in here? Everything basically falls apart, so that at the end, E comes out of the integral. So let me go back into something to write with. At least maybe use the blue since we use the blue. So E comes out of the integral, and it's a scalar, and it's just the integral over the area, the lateral surface. Because I just argued the other ones will not have, probably I did not, but this surface will not have any contribution. It's pointing this way, and I just argued the electric field needs to be pointing away from it. So there's a 0 degree, 90 degree in here. Cosine of 90 degrees is 0. Because E is pointing this way, the area is pointing this way. So this is a 0 contribution. This one also is a 0 contribution, although it's probably a negative 0 contribution, which doesn't make much difference. Okay, cosine of 90 degrees is 0. So the only place that is going to contribute is actually that surface. So the lateral surface, first of all, I'm going to add to the basis. So 0 from the two bases, 2 times 0, if you like, from the basis. But then I have the lateral surface now, which is E, which is on that surface, times 2 pi y times L. Okay, so this is the flux of the electric field, and the other side is actually the charge enclosed divided by epsilon naught. And sure enough, this answer does not depend on L for the electric field because it's made up thing. It doesn't exist. It's not part of this problem. Of course, the 0 there doesn't contribute, and now all of a sudden, the electric field E is going to be simply lambda over 2 pi times epsilon naught times y. If you're curious, trying to express in terms of the length of the wire, if it's not finite, if it's finite length, and you're not too far from it, you can use Q over L in here to find it, and that's Q over L, and this is Y, is how far you are from a wire. This is basically how you use Gauss's law to argue based on the symmetry of the problem. Okay. Mr. Newton, when he discovered his universal law of gravitation, okay. First of all, the item of the discussion now is that basically you have the steps on how to solve problems using Gauss's law is the following. This is the item basically I want you guys to remember today for the discussion. Is the following. First of all, you're going to find the symmetry in the problem. That's step 1. Symmetry. Because it looks like probably we're not going to get to the second example in here. Second, invent a surface. Choose a Gaussian surface. Here, identify. And here, you choose a Gaussian surface. Okay. 3, apply Gauss's law. Okay. And 4, which is very important, make sure that any invented parameters do not appear in the final answer. Okay, here is the deal. E depends on lambda, which is the charge distribution, how much charge you're going to put per unit length. 2 pi epsilon naught, that's the medium. Y in this case is how far you are from the wire. Okay. We could have done this calculation, and actually sometimes I used to do it in the past, especially when we are live, using the integral, and we'll arrive to the same thing. And it's going to be a little bit of an integral that involves trig functions, but at the end you're going to get the same answer. Okay. But this is a lot faster, but you have to know the symmetry of the problem. This problem has cylindrical symmetries. That's why I use cylinder. So we still have about 10 minutes. Let's see if we can get to the sphere. I was saying that Mr. Newton, basically, after he arrived to the law of universal attraction, took him almost 40 years, basically, to invent calculus and argue for the why he chose the apple, the distance, basically, for his law of universal gravitation. In the formula for the apple, for example, how to find the value of G, was just not just how high you drop the apple, which is about 1 meter to 2 meters, but rather the radius of the Earth, because he knew that the people were going to criticize his work. So he had to invent calculus, and in doing so, he basically made the discovery for the law of universal attraction. I mean, he knew the correct answer, but he didn't have the proper tools for it at that time, so he ended up basically inventing calculus for it. So you have to thank him for that too, okay? So, a sphere. And that is exactly this problem, but except we're going to be doing it for the charge, okay? So here is a sphere, and it has a uniform distribution of charge rho. I'm trying to find the electric field now somewhere. So this sphere has a radius big R, okay? Somewhere at a distance R less than big R. And I'm also curious trying to find the charge, the electric field at a point R greater than R. So I'm looking at the case when R is less than R, trying to find the electric field, and I'm also trying to find the electric field at the distance R greater than big R, okay? So here is the situation here. So the first case, because this is a spherical symmetry, so I'm gonna choose a Gaussian surface that is also a sphere. So here is a sphere of radius R. Both R and the sphere, in this case, the R is part of the problem. So the problem may depend on R. So what I'm going to say in this case is, by the way, that charge distribution is uniform. So that means that rho is equal to the entire charge for a sphere. This is a finite sphere divided by its volume. And the volume, as Martin earlier mentioned, for a sphere is actually 4/3 of pi r cubed. Okay, r cubed for the volume of the sphere, because it's a big sphere, okay? For a finite sphere, it's going to be different in there, okay? The surface of a sphere is going to be simply 4 pi r squared. If we're looking at that surface, but for a small square, the surface is going to be this much. As a matter of fact, I'm going to make the same argument as earlier before, and argue that the electric field must be radial, because if it's not radial, if it's pointing one way or the other, and I ask you to close your eyes, I'm going to turn the sphere one way or the other, and you're going to see that the sphere did not change, whereas where you pointed it is going to change, okay? So in this case, again, the electric field must be radial. That's number one. Number two, it's the same value on the entire sphere, because its charge distribution is uniform. Therefore, in this case, the electric field also should not change if I rotate the sphere one way or the other, because as far as you're concerned, the sphere did not change in shape at all when you opened your eyes. It's the same thing. It has the symmetry. So the effect should not be the same. So in other words, the electric field in here, everywhere, E is radial by symmetry, and also is the same on a sphere. Having said that, then on this Gaussian sphere, where the integral is, E is going to be just coming out of the integral. All I'm left with is the area of a sphere. And the area of a sphere in this case is 4 pi r squared. Okay? So that is one side. So I resolved the dot product because of the fact that the area and the electric field are pointing in the same direction. Both of them are radial. And I resolved also E out of the integral because the electric field is the same on this sphere of radius r, which is taken to be less than big R. is equal to the charge enclosed divided by epsilon naught. And the charge enclosed in the volume R is going to be Q, in this case, is going to be equal to the charge distribution times the volume on that sphere only. We don't count the ones that are outside. So on this one is going to be 4 over 3 pi r cubed. So if I plug in the value in here, it's going to be rho times 4 over 3 pi r cubed. Cancel the r squared and the r cubed, and you'll be left with, and if you like the 4 pi, don't cancel the 4 pi yet, because there is a reason why I kept them in there. So the answer is going to be E inside is going to be equal to rho, and rho, remember, is equal to Q over 4 pi r cubed, and I'm going to put the 3 upstairs, okay? So, and the 3 cancel the 3 here, and the 4 pi cancel the 4 pi in here, and the r cubed will be left. So I'm going to be left with a Q instead of that, times this 4 pi will stay 4 pi in here. Please check the algebra in here. Make sure that I'm not doing anything wrong. Divided by r cubed. This is constant in a sphere. The only thing that matters in here that depends linearly with distance, how far you are from the center of the sphere. If you are really smack on the center of the sphere, the electric field is 0. And as you move along all the way to the edge, the electric field starts to grow as distance only, as r only, okay? Now, if you are outside of the sphere, the initial argument will hold true, namely that the electric field on the entire big Gaussian surface, because I'm going to choose a different Gaussian surface, which is surface of radius r bigger than r. And in this surface, the electric field also must be radial and must be the same everywhere on the sphere for the symmetry of the spherical symmetry in this case. Because if you argue that it's pointing not on the radial direction, I'm going to just turn the sphere one way or the other, the original sphere that has the charges, and you wouldn't see that there was a changes in the charge distribution. So the effect in this case, which is the electric field, should not matter. So if you change it now, the electric field will change actually with it. So it should not, because it's a spherical symmetry. So the only way to retain that symmetry if the electric field is actually radial. Okay, so the electric field is actually radial by symmetry. And also it's the same on the entire sphere, because if you argue if it's this many newtons per coulomb on one side and this many newtons per coulomb on the other side, then I'm going to rotate this one and the values will shift on you, and all of a sudden your numbers start to change. Okay, so again, the number must be the same by spherical symmetry. So on one side, it's going to be E, simply E, no vectors in it, because the dot product will result just E, times the surface of the sphere, which is going to be 4 pi r squared. This is outside now. On the other side, the charge enclosed is going to be cube. End of the story. There is no other charge enclosed in here. It's the entire Q. So it's going to be Q over epsilon naught. So this is outside then. E is equal to Q over 4 pi epsilon naught times r squared. It looks like that of a point charge, but that's just coincidence in this case, because this is a sphere, solid sphere now. Okay, this is a solid sphere. Because in the other case was a little q over 4 pi epsilon naught times r, and it's radial. So if you want to put the vectors, you can put the vectors if you like. It's in the radial direction. Okay, so. When we meet on Monday, we're going to have to discuss the problem 55, which is really these two applications immediately, okay? And then do calculation on problem 52, because I gave this problem actually in the past as exams too, so you really need 52, by the way, and 61, and there is another problem, 47, they are similar. If you know how to handle one of them, it's maybe the geometry is a little different. It maybe the stuff is a little bit different. In the problem 61, it's actually you have concentric, or you have a sphere with non-uniform distribution. It changes actually in the middle of the sphere. Okay, so you have to handle that. You have to know how to do those integrations and stuff like that. Okay, and then as I promised, probably at least one of those problems, 53 and 54, and maybe we go in depth with it.
All right, fair enough.
Okay.
Have a good rest of your Wednesday.
Thank you, Professor.
Have a good day.
Thank you.
Okay.